Hello, good afternoon, everyone. So today, we have already seen the how the wave propagation is happening through the monoatomic chain, like simple monoatomic crystal, then the diatomic chain. Then we have seen for the mass in mass chain, and also the inertial amplifier and negative stiffness devices. So now let's see that thing, like how we can able to code those things. If we can try to see that how we can able to write that thing in MATLAB and all those. So like let's today have a discussion on that thing so that we can able to get the software based thing and we can get a more feeling that how these things are coming. So you can see that is the MATLAB interface of that. So here we are just inputting all the different parameters, like we are giving the mass, stiffness, then we are calculating with that again the mass. We are so here, and then the computation is starting. So we are like first defining what is the frequency ranges, and we are also putting some sort of storage for that, and we are writing the, so here you can see we are writing the dispersion equation primarily. So this is eta square, so 1 minus eta square with cos inverse. So that was the main dispersion relation. So we have written it that one, and you can see we are storing the imaginary part. So if the imaginary part is 0, then we are storing as the mu stored absolute this, and if and else once the the imaginary part is non-zero, then we are storing it that way. So with this we are like so in this case you can see what we are primarily doing. Once the imaginary part of the mu is equal to 0, that means solution is purely real, so wave should able to propagate. So in that case we are storing the mu in the positive value, and once the mu is negative, once the imaginary mu is not 0, positive or negative, whatever the value, then we are storing the absolute of the imaginary of the mu with a negative value. So that means in the positive side of the axis we will get the real part, and the negative side will show the imaginary part. Agreed? So that way we can write that portion and we can able to do that. So now if you see that we can run that program, and you can see that we will get the graph. So here important thing we need to notice that oh, mouse can be seen. Okay, so you can see here in this graph, you see this line is my 0 line. So that means this portion is the positive part and this part is the negative part. So this first thing is telling we are having that portion like going up, and you see that after the frequency ratio 2 we can able to have the propagation band, and after that the attenuation will start. So I have not plotted the attenuation portion here. So accordingly we can able to get this one also. Now after that you can see if we are trying to calculating the phase velocity, that phase velocity here is 1, and then the phase velocity is slowly decreasing. Now here once we are going the group velocity, you can see that group velocity near the band gap is becoming 0. At the onset of the band gap, group velocity is becoming 0. Okay, so you can also write this type of way. So that is for the monoatomic chain. Now okay, so if you see here, now here what is happening, now you can see here that we are plotting for the negative mass in mass, mass in mass system. So you can see that real value is goes up to certain value, and then the band gap is started. So you can see that we are having the imaginary portion started. It at the frequency ratio 1, it is showing the dip, again it is going down, and then in this portion, look, imaginary is 0 and we are getting the real value. So this is going this way, and then we are having the imaginary value, means the real value is becoming 0 or pi. So now we can able to see that imaginary is now, we can able to see that decaying thing again happening. So this way we can able to write and run these things. On the other hand, if you see the negative stiffness one, so here also you can see that is like little bit complicated plot. So here you can see that previously the way we have plotted, like we are having real portion of the frequency and imaginary part of the frequency, because imaginary part is always plotting in the negative portion. Okay, and again we are having a propagation band, again attenuation band. So attenuation band, these two are the propagation band. Now once we are having these two propagation band, and we can also able to see like how the stiffness is changing. So you can see that effective stiffness is changing like this way, that, and we can see here the stiffness is becoming 0, and this portion the stiffness is negative. So 0, it is corresponding to here, and where the band gap is started, or no, sorry, where it is actually getting high value, and here the effective mass is remain constant. This is the flipped plot of the real part of the Brownian zone. So here you see that this portion is taken. So here only the real part of the of the mu plot is there. So it is from 0 to pi, and then what happening, next limb you see, but next limb actually it is always going from pi to 2 pi. So here it should be flipped. So therefore you see that this portion is like flipped way, means it will be coming like here. So that is this way thing is happening. Now you have to take the phase velocity from that, like you have to go like this way, otherwise your phase velocity will coming wrong, phase and group velocity both will come wrong. So we can do this way, and we can see most interestingly, you will see that phase velocity is always positive, but here look, group velocity again near the band gap becomes 0. Look, here it is becoming 0, here this is also almost the onset of the band gap. Look, 0.61, 0.614, that is also 0.61, almost like close value. Then here if you see 0.101, more or less, you see. So that portion we can see that in both the cases the group velocity is becoming 0, but more interestingly here in this part the group velocity becoming negative. That is very important point. That means your packet of the wave is moving in the opposite direction. Instead of moving it in the positive, it is moving in the opposite. Like your, if you are giving a sinusoidal excitation, you will see that your pulse is moving in the forward direction. But if you give some other type of excitation, like suppose modulate wave packet or something, you will see that packet is moving in the negative direction, but wave is moving at the positive direction. That type of contradictory phenomena you can able to see in those portions if you are exciting it in that frequencies. Okay. So that actually like what I has to show you guys for this thing. Mono driven. Just a minute. No, this is damped. That I will need later. Okay. So any question up to that? No question. Very good. Now we have seen also like how the waves are actually going and how the dispersion curves can be generated from the MATLAB also. You can definitely try it by yourself. the coding. So now if we look at previously so that was the generalized monocouple system, and we have started discussing that in the last class, and we were thinking that okay, how these things are actually going and how the dispersions will be happening in that. Okay, so do you guys remember what is the definition of the monocouple system? Or like for example, we are calling this as a generalized monocouple. How does that qualify as a generalized monocouple, or what can be a monocouple system? One degree of freedom. Good. Could you a little bit more? Because there are so many degrees of freedom. Where one degree of freedom should be? 2 unit cells. Yes. So the point is that once we are choosing a unit cell, and then the unit cells are connecting to the other unit cell, then other unit cell, like this way the unit cells are connected all together. So in that case, that connection is maintained by a single degree of freedom. Here there is a very important point we need to remember. Suppose if I ask a unit cell something like this, let's say, how many degree of freedom? Is it a monocouple? Look, where the confusion can occur. If I cut it like this, what I will say? It's monocouple. If I cut it like this, suppose A dash, B dash. So if I cut it A dash, then definitely as per the definition, I should say that is a monocouple system. But if I cut it to B dash, then is it monocouple or not monocouple? Or bicouple maybe. Which one is correct? Means if you see B dash, if I cut, that can be also a unit cell, because if you remember the definition of the unit cell, you can say that yeah, we can repeat it. If you repeat that portion, it will also make that full chain, no doubt. So is it become a bicouple or monocouple? Bicouple? Yeah. Now, okay, if you think that this is a bicouple, if I cut from B to B dash, which seems correct, but if it is correct, then think, what will you call the full chain? Because it's a same thing. System does not know where you are cutting it. System does not know that are you cutting it in A dash or B dash. That's your choice to cut it. But which should be the more realistic representation of it? A dash or B dash? Here actually, Professor Mead, he proposed that whatever is the minimum, that should be the, means we can call that system as the that coupled. Like suppose if there is something like 3 thing is getting connected, then we should say it to whichever is minimum. So here this is monocouple system. So as per Mead, whatever is the minimum, whatever is the minimum coupling. So here this thing is becoming monocouple. Okay. So that also tell that we cannot randomly cut it. we need to be careful once we are cutting, that we should not cut where, means we should cut it where the connection is minimum. There only we should cut it. Okay. Otherwise, if we cut it, it will be wrong. Okay. Nice. So if that is the case, then okay. So now the theory of the monocouple system is actually coming into the place. So what it actually tells. So here we can see the few important point. Now suppose if we can able to get okay. So in this case, how we are proceeding. So first, so once we are making our unit cell, so once we have choose our unit cell, so now unit cell has been chosen. So now we choose the unit cell. So from there we need to make the mass matrix, stiffness matrix. Okay. So how we can make that? So if we think that this is my structure actually. So if I just draw it, to draw. So maybe I just go to the other slide. Or why not? If I can just show it in the very basic, and then we can go ahead. But yeah, okay, nice, we can do it. Nice. So if you see, just let me just write down the note number. So the note numbers are okay. So these are the 8 nodes we can able to see in that. Okay. So if so, our first target is to write the dynamic stiffness matrix of that full thing. How can we write the dynamic stiffness matrix? That is K minus m omega square plus L. Okay. So what is in the K? K it is, okay, so there is, so if you think this is m1 by 2, this is m1 by 2, this is m2 by 2, this is also m2 by 2, this is ma, this is ma, and this is m3, this is also m3. Automatically k3, k3. Is that visible? Visible or not? Visible? Huh? कुछ So if I just write it, m1 by 2, m2 by 2, k2, k3, m3, ma, ma, k3, m3, m2 by 2, k2, I think k2 by 2, and m1 by 2, this is k1. So like this way these things are coming, so we can able to have the mass and stiffnesses like this manner. Now if you think, what is my dynamic stiffness matrix? So my dynamic stiffness matrix dy equal to k minus omega square m plus L. Okay, so in that what should be my k? So okay, just put the node number also. Node number is 1, 2, 3, 4, 5, 6, 7, 8. Okay, now if you think, which are the nodes will get condensed? 3, 4, 5, 6. This node will get condensed because they are not connecting to the sides, so they will not be no longer be there. So we should write the condensed dynamic stiffness matrix for only the 4 nodes, 1, 2, 7 and 8. Agreed, all of you? And if we see, so now if I just write the equations for node 2, or maybe just I will just change the little bit. Instead of this is 7, let's make this 7 and this 8. So we are like connecting the last two. So node 2 and 7. So node 2 and 7, if we think, what is the equation of motion? m2 by 2 into u2 double dot plus k2 by 2 u2 minus u1, that is equal to 0. Agreed? Because this motion, that is just connected by a spring. I just writing the equation, simple. That is for 2 and for 7 also, m2 by 2 u7 double dot plus k2 by 2 u7 minus u8, that is equal to 0. So that's the equation we can get for node 2 and node 7. Okay, now if I think, what happens for 4 and 6? So node 4 and 6, what will happen? Node 4 and 6, it will be m3 v3 double dot plus k3 into v3 minus w3, that is equal to 0, and m3 v6 plus k3 into v6 minus w5, that is equal to 0. Okay, so now you can see these two equation is relating node 2 to 1 and node 7 to 8. Okay, and this relationship gives me what? Sorry, v4. Okay, what happened? v4 w5. Yeah, this will no, yeah, this will be 4. And then W3. Makes sense. Yes, you are right. So then in case of the node 5 and 3 or 3 and 5. Node 3 and 5, what will happen? Simple, you can think. This point is there, we are having these two forces, maybe we can think Fn, and this point is giving the inertia backward direction, that is ma into W3, and this spring will give the inertia, that is K3 into W3 minus V4. Okay, so what will be my equation of motion? ma W3 plus K3 W3 minus V4 plus 2 Fn sin phi, that is equal to 0. Agreed? Similarly, what can I write for this one? W5 minus V 6 plus 2 Fn, that is 0. So I get node 3. So if I see 2, 7, 3, 4, 5, 6, all I got except 1 and 8. Okay, because 1 and 8 is my central node and they are actually connecting both the sides. So that's the the monocouple system actually, and other things are like auxiliary things are happening. So here once we have connected that way, you can write, and now we have also the auxiliary equations. That is what, if I think, that is my V W is with 3 and U. The EM I have written what? So I written W. This is W, this is Z. No, this is W, this is V. Okay, and this is U. So okay, just a minute. So now if you see that W3 should be equal to how much? W3 should be equal to U1 minus U8 divided by 2 tan phi. That we have done in the previous classes. We have seen that if that rigid link is moving, then from the kinematic equation, how we can able to establish it. And we have also known that this is like for the small deformation. We are neglecting the large deformation so that the rotational terms and also the sine cos is actually neglected and higher order are neglected. So we are having this thing. So now with this help of that full thing, what can we do? Now we can club the full thing and we can write our matrices, that is with U1, U1, U2, U7, U8 double dot plus so how we should place that? So M1 by 2, M2 by 2, M2 by 2, M1 by 2, and rest will be 0 because the masses are lumped at the nodes, and here it will be K1 plus K2 by 2 minus K2 by 2 minus K2 by 2 K2 by 2. Here also K2 by 2 K1 plus K2 by 2 minus K2 by 2 minus K2 by 2, and we will have plus ln, and we will have ln here, ln and ln, minus ln minus ln. That ln is actually coming from the coupling, whatever we are actually not neglecting, condensing. Like if you see that full part we have condensed out, we are no longer taking care that W3, and like here, from here what we are trying to do, from here actually we try to write W in form of, or maybe W in form of V, and then we substitute or solve it here, and we are writing everything in terms of the U. In terms of F we are getting, and then also once we are solving for then 1, I should write the equation for 1 and 3 that we have written also in the last class. To see, yeah, that was the question for the first and second cases, so those things are already there. So like once we are calculating the Fn, we can able to substitute that Fn back, and we will get this. And what is the ln basically? So ln is actually coming 1 by 2 tan square phi into K3 minus ma omega square minus K3 square into K3 minus m3 omega square into U8 minus U1. So this portion is fully your ln. I'm sorry. Yeah. So that part is actually coming like so. So this is my force. So once you are writing that force, you will get like this way, or Fn cos theta basically. So this is the matrix we are getting. Okay, so this matrix is my dy matrix. So that is the not dy matrix. So we are getting, yeah. So now, so that way we will get, and now once we are writing the D matrix, so D matrix we will write like so. This is my mass, this is my stiffness, and this is some L matrix, which is like basically the connection of the forces, because that links, they are giving the force cell connection. So, and that is also frequency dependent, so we have to put it there. So now dy is becoming K minus m omega square plus ln. So that's my D, this is L, sorry, this is L matrix. So that way we can get my K matrix, sorry, dy matrix. So once we get the dy matrix, now as we so we can see that yes, so in the D matrix, so in the D matrix we can rewrite the full thing in the like U1, U8, U2, U7, and full things would be equal to 0, 0, 0, 0. No, not 0, 0. That will be F1 and F8. Because if you see what is happening now, like you have, I'm just drawing it something in between, which is basically condensed here. Okay, so that is my node 1, that is my node 8. This is 2, this is 7. Okay, and in between, this is not just a simple spring, it's just like a completed, means the complicated matrices is there, and that's giving the connection from these two, and I am applying the force F1 and F8. Yeah, because that's like an element. If you just think like we have a spring mass, if you just apply, so you are applying the two forces, and we are not applying the forces on the resonator because they are within that degree of freedom. They are not independently connected. They are just attached to the degree of freedom. Okay. So here if we see how the matrix looks like, that is like omega square m1 by 2 plus k1 plus k2 by 2 plus ln, so yeah, minus k2 by 2 in the next one. So like this way, that it's a complicated matrix is coming fully. I am not writing that full matrix here. You can refer the paper or book, or yeah, I can actually show that one also. Okay, so if we are coming back to the our IA-NMNS system, which is like a basic generalized monocouple system. So you can see that the system is looking like this. So here it is very clearly demonstrated that these masses are connected, and this is the main chain. So our wave is going in that direction, and these portion are like auxiliary connected, and this MA can move vertically up and down. This mass M2 can also move vertically up and down, and that is connected with the spring stiffness K2, and these green are the rigid links. So now if we think that if we try to write the equation of motion for node number 7, we can write m1 into u1 double dot plus k1 into u7 minus u8 that is equal to 0, and similarly u2 also can be written like m1 u2 double dot plus k1 into u2 minus u1 that is equal to 0. Okay, and then if we are writing the equation for node 4 and 5, then so that is primarily the attached resonator. If we are writing the equation for these two, so you can write m2 v double dot v4 double dot plus k2 into v4 minus v3 and m4 m2 into v5 double dot plus k. So this way we can get these two equation written. Now node 1 and 8, now we try to solve for node 1 and node 8. So here we can see these two, because here you can think that once we are drawing for node 1, we can have these two forces, that is Fn, this is Fn, and that will have m into u1 double dot, and this one will also have k into u1 minus u8, and also that spring force, that is k1 into u1 minus u2 will coming into picture. So that's why we can able to write it this way, that equation can come here. And similarly, once we are writing for node 3 and 6, then what happening, here also we are having Fn force, here also having Fn force, and this movement is upward direction, so that will give the inertia force in the downward direction, that is v6 double dot, and we will have the spring stiffness k2 into v6 minus v5. So we can see that way we can write the complete equation of motion. Okay, now what we do, now next step is the compatibility equation. So we can write the displacement of node 3, displacement of the node 3, we can write v3 equal to u8 minus u1 divided by tan phi, and these two, because that link is the rigid link, and due to its movement they are constant equation. So these are constraint equation, okay, and from that, like we can actually substitute those things and we can calculate whatever is the force. So now we can write the force in terms of the u8 and u1, okay, and also on the other side how much force is coming, that also you can able to get that too. Okay, so now we can combine that full thing into the dy matrix. So dy matrix we can write like this way, where the stiffness matrix like k is this, mass is this, and displacements are u1 u2 u7 u8, u1 u2 u7 u8. So we are just choosing this, and all those we have actually condensed in the L matrix. So L matrix in terms of the force, we have seen that once we are doing this one, there is a two force term, and these these force terms are actually containing this degree of freedoms. So whatever is coming from there, they are actually considered in that force term. So that force is actually coming here in terms of the yield. Okay, so you are writing that way, and then the dynamic stiffness matrix can be obtained. Is this so? Dynamic stiffness matrix is basically do what? So once we are writing our equations like we have mass matrix, stiffness matrix, and some force, then we can condense the full thing and we can write as a dynamic stiffness matrix that thing. And so that dynamic stiffness matrix will be equal to our forces. After that it can come. So here the dynamic stiffness matrix is coming like this way, and now necessary matrix multiply and the static condensation we have done from node 1 and 8. So how we did that part? So if I think like how we are going from here to here, so we have this matrix. So here you can think this is u1, u2, u7, u8. What we don't need? We don't need these two. u2 and u7 we don't need. We need only u1 and u8. So what we have to do primarily? So once we need these two, we can first actually rewrite the full matrix in this form, that we have u1 and u8, u2 and u7. So basically we have changed the row and column. So accordingly, and there will be the forces F1. So this is 0, this is 0, and this is F8. Okay, because you can see here we are not applying any forces here and here. Okay, we are just only applying the forces here, F1 and F8. If you remember, once we have shown how we are solving the unit cell, once we are solving the unit cell, there are the two ways to solve it. What are the two ways? If you just go back, or we can just do it here. So we saw that, like suppose once we are solving the monocouple chain, we saw that this is, let's say, un, this is un plus 1, and this is un minus 1. So we write un plus 1 equal to un e to the power of I mu, and un minus 1 equal to un e to the power of minus I mu. Okay, I mu is, that is nothing but the wave number into displacement. Okay, so we can write like this. We're not into distance, the lattice unit. So we can write that way. So we can substitute that two things here, and we can write it, or what we can do, we can make the unit cell like this maybe, and we can say that okay, this side we are applying some force F1, this side some force F2, and we have the displacements like un, and here it is like un plus 1. So this is Fn, this is Fn plus 1. So what happened? And we know that Fn plus 1 should be equal to Fn e to the power of I mu with a minus sign has to be put, because that the continuity has to be maintained, like whatever the force is coming here, and if we are putting the other unit, that force will be opposite side, this will be okay. So we have to change that sign and we can input it. So that we have discussed in the very first class. So accordingly we can able to think it. So here F1 and here F8. So here F8 also need to be opposite direction has to be done. So this way we can actually write that thing. Yeah. So now once we written that way, so what happened? This will go here. This will go in the second one, like 1, 2, 3, 4, 1, 2, 3, 4. So you have basically changed that. So here whatever is like, so this row and this row will actually be flipped up and down. So this way we can write it, that full thing, and also that columns also need to be shifted. So we will get that. So here once we get this thing, so you can see that this is my S11, this is S12, S13, S21, S22. Matrix is coming like this way. There is force 1, force 8, 0, 0. So how we can do the condensation? If I write it in the matrix form, so S11 into, I'm just thinking this is my two boundary nodes, so UB, and this is two internal node, UI. So S11 into UB plus S12 into UI, that is equal to F boundary and F internal, or that is 0 basically. So F boundary and S21 UB plus S22 UI, that is equal to 0. Agreed? Now in this case what we can do? So we can write, so what we need to omit? We do not need the internal, because internal degree of freedom is not connecting. We cannot able to implement the Bloch theorem in the internal degree of freedom. So we should not need to take the internal degree of freedom, we can leave that. So what can I write? Ui equal to minus S22 inverse S21 into AOB. Okay, and if I substitute back into the main equation, so S11 plus, not plus actually, S11 minus minus S12 S22 inverse S21 into UB equal to FP. Got that? So what is this? So this is like a condensed dynamic stiffness matrix. What I actually wrote it as a DYC. There is a dynamic condensed stiffness matrix, and that is multiplied with U1 U8 is giving me the force F1 F8. Agree, all of you? Agreed? Okay. So if so, up to that point, any doubt? Like how we are condensing the matrices and how we are coming into that point? No, very good. So now once that thing is done, then we can try to calculate the receptance matrix. Now receptance matrix is what? That is the inverse of the dynamic stiffness, condensed dynamic stiffness matrix. So this is nothing but the inverse of that. Obviously, please don't ask me to do the inverse. That you can see it's a so complicated thing to do it here. Although it is A, B, C, D, so you should write it. You can able to do that easily, not a big problem, but still it's quite complicated, quite big numbers are there. So we can do it like this way. So here, once we will do that, what can we get? We will get this way. So what does it tell? So it tells me, so now if we think, I have DYC into my D matrix is equal to my force. So what is my DYC? DYC is my dynamic condensed stiffness matrix. What is D? D is nothing but U1 U8. What is F? F1 F8. All of you agree? Now what do we do? We inverse it. So basically we do that, and that is my receptance matrix. Agreed? So what receptance matrix is telling me? That is D left, D right should be equal to my receptance matrix times FL FR, and here it is alpha LL, alpha LR, alpha RL, alpha RR. And what is the Bloch theorem? We know Bloch theorem is DL equal to e to the power of I mu DL, and FR equal to minus e to the power of I mu FL. Why that minus? Anybody? Come on. why block theorem gives in the fourth term minus? We discussed those things. Exactly. Because displacement is maintaining the continuity at the junction. At the junction, both the displacement are same. Like for example, once you are making the chain in this node, like if I say this is FR and this is FL, this, I'm sorry, UR and UL, UR is equal to UL, but FR equal to minus FL, where that force should be balanced and displacement should be equal to maintain the continuity. So therefore, force becomes minus and displacement remain in the same, that is not minus. Okay, so we can get this way. So now if I write, so now what we can do, now we can write dr, so I can write it dr equal to alpha RL into FL plus alpha RR into FR. And that should be equal to, now if I just substituting this one, I'm just working on that. So dr equal to this and e to the power of I mu times dl, that will be alpha LL plus alpha LL FR plus alpha LR, that is L, and this is R. If I just write this equation, dr equal to e to the power of I mu times dl, I substituted dr equal to this and dl equal to this. Okay, from that two equations. Agreed? Nice. Now next thing is that I will substitute FR in terms of FL. So what I can get? Plus RR e to the power of I mu with a minus sign here, and this will become FL. Okay, should be equal to e to the power of I mu times alpha LL minus alpha LR e to the power of I mu times FL. Agreed? Now if you see both the side, so if we can also you can go one step further. Means first we can divide it with the e to the power of I mu and we can write it. So e to the power of minus I mu this plus minus e to the power of RR. So if I just dividing it, so that will be cancel out, minus alpha LL plus alpha LR e to the power of I mu into FL, that is equal to 0. Okay. So what is 0 here? Obviously FL cannot be 0. If FL is 0, then full thing will be 0. That is a trivial solution. So non-trivial solution tells me that this should be 0. Okay, very good. If this is 0, that means what? Okay, so you can see that this thing is equal to 0. So what can I write? What is my objective? Don't forget the objective. As you are solving any mathematics, because most of the cases we happen that thing that we forget what is our goal. What is the goal? बताओ यार. Huh? Dispersion diagram. Yeah. So we need to establish the relationship between mu with omega. Where is omega? Anybody? Where is omega? Yes, within the alpha. Exactly. Why? Because alpha is nothing but the dynamic stiffness matrix, and dynamic stiffness matrix must contain the omega. So omega means the excitation frequency that is within the dynamic stiffness matrix, and alpha is actually the receptance of the dynamic inverse or the receptance of the condensed dynamic stiffness matrix. So that contains the omega, and e to the power of I mu we can see here. So which is the wave number or the non-dimensional version of the wave number. So our target is to get mu in terms of omega. Okay, so we will have this thing. So we can write it e to the power of I mu minus I mu alpha RL plus alpha LR e to the power of I mu should be equal to alpha RR plus alpha LL. Now here there is a very interesting thing. You see alpha RL and alpha LR. What does that mean? Alpha RL and alpha LR. And if you think this is the part of the receptance matrix, that means what? How we can able to feel that? Feeling of this we can think like if we are not applying any force in the FL, only applying the force in the FR, how much displacement we can able to see in the FDL. Means suppose L naught R naught, I am applying a force here and how much displacement I will get here. How much displacement I will get here. That is alpha LR. And how much force I am applying at the R and how much displacement I am getting at L is alpha RL. That's the primarily. We can think that way. Okay. So what is happening here? So, should they be same? Why? That's the reciprocal theorem. Exactly. So from the reciprocal theorem, we can say that they should be same. There could be some problem if the lattice is non-reciprocal or some other things. Then maybe that thing will no longer be remain same. But for the standard monoatomic chain, this thing should always same. Okay. If you have some active control devices in between, some electrical signal is going this, that side, there could be a possibility that this thing will no longer remain same. But in the passive devices, once the lattice is like a conventional type of lattice, this thing will always be same. So from there, what can I write? LR or RL, whatever, they're same. Okay. And this thing is nothing but 2 cos mu okay. So cos mu equal to RR plus LL divided by 2 lambda LR. Yeah, in the receptance matrix, we can see another very interesting things as well. That is, if we try to feel what is lambda LL and lambda RR. Now think, what is lambda LL? If we are not applying any force in the R, how much deflection will we get if we are applying that node, force on that node? Exactly. That is lambda LL. If we are applying the unit load, how much will be the deformation there? And otherwise is lambda RR. You will see they two also will remain same. Means these two will be equal and these two will be equal. So this one will be eventually become, once the matrices are symmetric. So this is happen only when your mass matrix, stiffness matrix are symmetric. And if you see, most of the cases our mass matrix, stiffness matrix all become symmetric. They are not asymmetric. So this thing will automatically be happen if the matrices are symmetric. So we can get cos mu equal to this thing. Okay, so any doubt on that? And interestingly, you can also see, so here maybe I will just write it down. So if you see for this structure, if we try to calculate what will be the lambda LL. Lambda LL, first person let me write the denominator, so numerator will be minus omega square capital M plus Q1 K2 by 2 plus ln plus K2 square divided by 2 omega square M2 by K2 divided by dyc, and lambda LR, that is equal to, that is simple, Q1 plus ln dyc. Now what is the mod dyc? Oh, that is equal to minus omega square m1 by 2 plus k1 k2 by 2 plus ln plus means that is, sorry, this is actually summation of these two, means this and this square, means if I just think this is numerator, this is the n1, this is n2, so this is n1 square plus n2 square. So that is my dy of c. Okay, so this way we can able to get that. And interestingly, we can see that denominator and numerator, so prime point is what? If we see all the terms like mass, stiffness, these things are there. Okay, and ln also we have discussed that that is nothing but condensing that force from that systems it is coming. So that is also containing mass and stiffness primarily. So here only one thing which is not the system parameter, that is your excitation frequency omega. Okay, so here this thing is primarily dependent on omega and this is also dependent on omega. So we can say that cos mu, that is the function of the excitation frequency, and we can get the responses from there. So any doubt in that? Okay. So actually later these things, like we also introduced it as like cos mu equal to g of omega square, because you can see this will be also proportional to the omega square, not only omega, because we are not having any damping here. If there are the damping, then only omega can also come into picture, otherwise only omega cannot come. It will be the proportional with the damping square. And after that, if you go ahead, so here actually, I mean, why we do all those things, and what actually we can able to get from here, that is, we can able to write that dispersion like that cos mu. One important thing is that cos mu can be written as like 1 minus omega square into effective mass divided by effective stiffness, that we have seen in the last class also, or in the previous classes. We have seen that once we are having the effective mass and effective stiffness concept, we can write the dispersion relationship in terms of the effective mass and effective stiffness. So that can be implemented here. And also we can write this thing as like a rational polynomial of the omega, like the numerator also has a rational polynomial of omega and denominator also have a natural polynomial of omega. And most importantly, if you see, once we were discussing about the mass in mass, like we have a mass in mass chain, in that case we have seen that once we are drawing our dispersion curve, that is like real of mu with frequency and imaginary of mu, we have seen that we will have a dip like this. Okay, and that dip has a peak, particular peak point we can able to see. We have also seen once we were doing with this system, we also had a peak, something like that. But once we were doing this one, like diatomic chain, that time we do not have this type of peak. That time it was like this. Now this essentially tells, means once we start analyzing this formation as like a rational polynomial, then we can able to identify when we can able to get the peak in the attenuation band and when we cannot get the peak in the attenuation band. And why that is important? Because if you see that mu, how the mu is actually coming, mu is basically like the wave, and so we are saying that if this is a, like if a wave is propagating into that, so we are writing like, let's say this is my u2, u1, u0. So like u2 equal to u1 into e to the power of I mu or ikx. So here once we are writing that, so this k could be real and imaginary. So this is the real and imaginary part of it. So once this real part, that is kr plus I into k I into x. So this way this thing is coming. So ui e to the power of I kr x into e to the power of minus ki into x. So what is this? E to the power of minus ki into x. This is nothing but the decay in the space. So this, now once that ki is increased, that means what? Your decay will be faster. This means your ki is increasing. That means you are having a higher level of attenuation. You don't need that many number of units to attenuate your wave. So once you are having this type of peak, that means in those frequencies wave hardly able to propagate. It may be just confined it into where you are giving the excitation. It get entrapped more or less into those places. And now suppose you have got this type of thing and you are somewhere here, you will see that it's going, maybe like you need like 50 units. After that you can see that it get dissipated. Like in real life, we don't need that many 50 units, but we do not have the space for that 50 units. So for the real point, there is some cutoff is required. From the physics point of view, we generally draw it at 0, but from the engineering point of view, we generally do not restrict it here. We generally reduced it at some point, because that practicality has to become. Means we cannot put that many number of units. There may be some restrictions. Maybe like you are making a wall for the building, let's say, and you are placing some units, and that unit may be like, let's say, 10 mm wide. Okay, and your designer or the architect told that you can only have a space of, let's say, 150 mm. Although 150 mm is too much. So how many you can put? Very simple, 150 divided by 10, 15. And so you have to draw a line in that which will correspond to that 15 number of units. After that 15, like suppose 16, 17 unit, you may be getting the attenuation. Mathematics will show there is attenuation, but that attenuation is not practically achievable with that range. You got that point? So here actually what we are getting directly from the physics output is changed in the engineering context. Got that point? Clear? Nice. Now the next thing is coming where? Yeah, so that's why the importance of K is very much. And often we try what? Once, like you can see that this type of units, like why we started this type of unit. So here you can see there is a 3-4 mechanisms are actually connected, coupled together, that they do the hybridization. So how the hybridization is happening? I can show you some of the pictures. More interestingly, what is happening here, you see that if you are not tune it properly, then what happening? Each of the resonators, just a minute, wait for 1 minute, desirable. So what we more desire, we can try to couple these two frequencies, and you see where is the advantage. Now you see in this region, look at the amount of attenuation, that is quite high. When there is a significant amount of attenuation you can able to achieve in a quite a significant amount of band gap. Here look, like in this rectangular area, your level of attenuation is really good. You can clearly say that in that rectangular region, minimum this much dB reduction you can able to get. There is no doubt. Directly you can say that. In any frequency, in that region, you are getting it. So this is something the advantageous, the hybridization of the resonances. Just the resonance does not make anything. You can see this is the condition, just the resonance. Small band you are getting, they are fragmented, they do nothing actually. But once you can hybridize the full thing, that's something what people are looking for. Maybe you are making something for the high-speed train. The train speed has a particular limit of the frequencies. Like let's say once the train is moving for 50 km/h, it creates some frequencies. Once it is moving 100, it creates some frequencies. Once it's moving 150, it creates some frequencies. Now, in the Indian railway system or in any railway systems, speed limits are fixed at particular position. More or less, this is the speed. So you can think that in those ranges, you have to put, or you have to attenuate the vibration for those portions. So that has to be catered by your design. There are some frequency, if it is missed, it makes no sense. Like let's say for like let's say this is the 50 kilometer per hour, and this is somewhat like 150 kilometer per hour. So we can say it can attenuate that full thing. We can say that. But here we cannot say that this can attenuate this, because these two portions are not attenuating anything. So suppose like train, like let's say this is 50 and this cuts around 100, again 110, then again 150. So what about the 100 to 110? In 100 to 110, if the train is moving, then the full rail track will be broken or something like that. It will happen, and that cannot be the solution. And if you see, we can only restrict the train to move above certain speed. We cannot say that you should not go between 100 to 110. That's something crazy. That way the things not happens in the real life. So that's why the importance is very much on having a continuous wider band gap instead of having the fragmented bands. Make sense? So that's why that is actually very important to identify how these points are located and where these are coming, and all those things can be actually seen from the basic theory of that monocouple thing. Okay, I think you got that idea that why we need these things. So we have seen that how we can able to plot the dispersion diagram, and also how we can get the band gap, what is the significance of it. We have also seen how the generalized monocouple system and also several other monocouple systems can be found, and how their equations can be processed and all. So now, but one of the most important points actually missed till to date, that is what happened if the system is of finite dimension. Because most of the cases, if we see in the engineering context, systems are finite in dimension. We are not getting infinite systems. So still the attenuation band or whatever we are implementing, the Bloch theorem and all those things are still valid, or there is some problem or some changes happened due to the finite dimension of it. And there are also the implication of the boundary conditions as well. Like for example, instead of having like a infinite number of chain, once we are having a finite chain, then there could be the boundary condition, like one side may be fixed or maybe free. So several different things can be possible. So what is the impact of that? Or can really a real finite system can also able to show that? And also, once if you see that the experimental validation of those theory also came from the finite system, because infinite system cannot be made. So how is that, or where is the changes, or how we can able to realize? So first, like if we think, like we have a, like let's think that we have a finite dimension of the chain. So like M K, like this way that full M and K chain is going on. It's a finite dimension. So previously it was infinite dimension. So once it is finite dimension, then what are the two changes? So suppose if I think infinite versus finite, our mass and stiffness, they will be remain same for both the cases, no doubt. What, and in infinite what do we do after that? We find the unit cell and we apply the Bloch theorem. That was the way we have done. So we make the unit cell and we apply the Bloch theorem. Now can we make the unit cell for finite? Yes, we can make the unit cell. Why not? So we can make the unit cell. Perfect. Can we implement the Bloch theorem? No, that's not possible. Because what Bloch theorem tells? Bloch theorem is telling that you are having a wave, and it is just basically taking one point and another point and maintaining the correlation. Now, this thing, if you are implement the Bloch theorem for the finite, that will be implemented only within the domain, not in the boundary. And what happened after the chain get finished, that thing cannot be modeled using the Bloch theorem. So Bloch theorem cannot be implemented for the finite chain. So that is not possible. Okay. So what we have to do here? So dispersion diagram directly not coming for the Bloch theorem. Means from the finite chain. But still, if we see, they are very closely matched. So let's see what exactly happening. So now just forget the metamaterial and everything. Just think like we have a structure. So we will have, instead of the Bloch theorem, we will have finite number of unit cells. So maybe we will have n number of cells, because it's a finite, and we will also have the boundary condition. That is also important. So let's say now if we are implementing these two things here, what can we say? So maybe we are like say that, okay, that is my boundary condition here. One side is fixed and another side it's free, let's say. Okay, I'm just numbering like maybe 1, 2, 3 up to n. And number of units are there. Okay, so how can I solve it? Now, as I told, forget metamaterial, forget periodic structure. You just have a simple multiple unit, n number of unit. How will you solve it? Multivariate freedom system, perfect, no doubt on that. So how will you do? You will make a mass matrix. Perfect. Mass matrix will be a diagonal matrix of M. Very good. Stiffness matrix, it will be. How will be the stiffness matrix? It will be tri-diagonal matrix. Okay. And what type of solution will you do? What type of thing will you do? Now think, what we have to establish? We have to see the band gap. So here we got the band gap like this. So band gap means the frequency where wave cannot able to propagate. Agreed? So we have to see here where wave cannot able to propagate. Does the two region matches with each other or what? So how we can able to do that? So for this, we need to excite the system and need to see. So for exciting, we cannot actually able to have it like this way. We have to excite it by some, like maybe u double dot or u dot, simple u. We can excite it. So if you think, we can put a shaker in that portion and we can excite it, and we can place some accelerometer in that point, and we can try to measure that acceleration, that how much acceleration is coming in that point. Or maybe we can point some LDV, laser doubler vibrometer, and we can measure that how much velocity is happening, or we can put some displacement sensor and we can measure how much displacement is happening. Okay, so we can do that type of setup, and we can try to measure that how much vibration is going to the end. Okay, so if that is our objective, then what we have to do? We have to apply the force at that first node, or we have so we can write the mass matrix into u double dot, that full thing, plus stiffness matrix into u, that complete thing, equal to all 0. Okay, because with the shaker, once we are giving the excitation, that excitation is coming like a displacement we are putting at some particular point, and that row will eventually come, that column will eventually come to the right hand side, and first row will be cancelled. Okay, so we will now have that condensed portion, this and this part is coming here. So we can solve that mass matrix, displacement matrix, and the other side, and we can able to solve it, and we can find it out how much displacement we can able to see in each cases. Okay, now if we are changing the frequency, then what happen? Then we can see that our like so that is known as the FRF, frequency response function. So you can able to see that once we do this type of thing, we can get this type of FRF. If we take a normal monoatomic chain, if we excite, we will see this type of thing is happening. Okay, why and how many peaks we can get here? Whatever is the number of unit. Why that many number of unit is corresponding to this? Yes, closed mode. Yeah, so these are the eigenfrequencies. In degree of freedom system, we will have n number of eigenfrequencies, and that eigenfrequencies, the structure will go to the resonance. So all the resonances you can able to see here, and then we will have a attenuation, and in the attenuation we will have no peak. Make sense? Clear? So in the real life experiment also you are doing, we will be able to see that, and where it is matching. So here it is the frequency axis, and here it is the amplitude axis, and this frequency and the frequency from the band, whatever is coming here, like, so this is the real of mu, this is imaginary of mu, and these two frequencies should be same. Got that part? That's a very interesting thing, and that actually validates that the theory of the infinite chain is also applicable for the finite chain as well. But there are some diversion or some deviations obviously happens, because obviously here you can see the peaks, the where the resonances are occurring, you can able to see. But in case of the dispersion, that point is completely not there, that is not present. So we cannot able to see those things. Additionally, the benefit is where and also, like, if you do for the mass in mass chain, in mass in mass chain also you can able to see like this type of thing will occur, and corresponding the dispersion, if you think, it will go. There's a dispersion diagram. So these points will match. Now there is a big like, we actually do several studies, and we also find it out that this thing depends on the number of unit cells. Like, suppose if you put 2 or 3 unit, that point will not come. You must have a sufficient number of unit so that you can get this point correctly. If you are putting less number of unit, this point may vary or shift. Okay, so if you just put a single unit, it will not happen, it will just go like this, something like that. It will not going to match exactly those points, because one unit cannot be called as like infinite unit, that's too much. So those things will not going to happen. That number of units plays a role, so that thing, and but after certain number of unit you can found that things start getting converging, then there is no problem on that. Like generally 6, 7 or maybe 7, 9, after that you will found these things are coming more or less pretty okay, you are getting a definite portions. There is no standard actually. That is something like you can think as like a finite element way. Like in finite element we have to do the mesh convergence, we need to find out that when the result is coming. Generally we generally do not do anything less than 5. If you see the first experiment of this chain, that is done in 2008. The journal of New Journal of Physics, that was published in there. I forgetting the name of that author. They did the first that small experiment, and they actually showed, they took I think 7 units, and they got that band very decently. It was more or less matching the full thing. So these are the things that are happening. So quite interestingly, these things are matching actually. And then several studies also people have done. They are try to putting the effect of the boundary conditions. They have seen, suppose if you have a fixed boundary, how it is happening, and it also depends on how the FRFs are changing, because once it is a finite thing, na, so you can actually check any FRF. Like for example, you are giving a force here and you are measuring here. Like you are giving the force here, you are measuring here. All those things can be possible, and those FRFs all are actually primarily giving the different style, but primarily you can able to see this type of bands. And some of the cases maybe you can see some peaks in the attenuation band as well, and that is something a very interesting study. Some of the time non-Hermitian systems also give the peaks within the band. That's often called as the surface mode and all those. Okay. So yes, so with this we can conclude the today's thing. So any question, by the way, up to this? Okay, so with this we can conclude it here. Thank you very much.